In section 4.2, we are going to start our discussion of logarithmic functions. Our objectives in this section are to change from logarithmic to exponential form, to change from exponential form to logarithmic form, to evaluate logarithms, to use basic logarithmic properties, to graph a logarithmic function, find the domain of a logarithmic function, use the common logarithm, and use the natural logarithm. All right, so let's define what a logarithmic function is. We're going to start by looking at the exponential function. In section 4.1, we defined the exponential function to be a function in the form f of x equals b to the x. So our exponent is what contains our variable. And we said that our base had to be larger than 0 and it can't equal 1. So it has to be a positive number and it can't equal the number 1. All right, we also looked at the graph of this function. And when we looked at the graph, we graphed f of x equals 3 to the x, but the shape of that graph is the standard shape of an exponential function whose base is greater than 1. And it looks something like this. And it intercepted the y-axis at 1. So we noted when we looked at the graph that this function is 1-to-1. And what it means for a function to be 1-to-1 is all the y values are unique. So if you have just a regular function, you may get the same y value from two given x's. For example, the standard quadratic function, you can input 1 and output 1, but you can also input -1 and output 1. So you can get the same y value for two different x's, and that's fine. That makes it a function. However, it is not 1-to-1. For a function to be 1-to-1, I can only output 1 y, no matter what I input for x. So this function is 1-to-1. And if it's 1-to-1, that means that it has an inverse, and its inverse is also a function. So let's find the inverse of the exponential function. As you recall from chapter 2, to find the inverse, the first thing we do I seem to have a share problem. All right, we're good to go now. All right, so the first thing we do is we replace the f of x with y, because f of x and y are exactly the same thing. All right, so we get y equals b to the x. And the second thing we do to find the inverse of a function is we interchange x and y, because that's what the inverse does. If I have a function whose domain is whatever it is, that becomes the range of the inverse. The function's range becomes the domain of the inverse. So to find the inverse, we interchange the domain and range. We interchange x and y. So what I get when I interchange x and y is I get x equals b to the y. And that is the logarithmic function. So the last step when we were finding the inverse is we solved this function for y. And that's going to be difficult for me to do here because I'm trying to find what the exponent is. When I raise a base to that exponent, I get some value x. So we're going to write this in a different form. We're going to write this in terms of a logarithm. So again, the logarithmic function, y is the exponent. You raise a base 2 to get the value x. The logarithmic function, y, is the exponent that you raise a base 2 to get a value x. So the way we write this is as follows. For x greater than 0 and b greater than 0, and b cannot equal 1. Again, our base has to be positive, and it cannot equal the number 1. But we also have to stipulate that x has to be greater than 0 also. Y equals the log base b of x is equivalent to b to the y equals x. They're exactly the same thing. Now you'll notice that this b right here is a subscript. And you remember what a subscript is? A subscript is a number that's to the right and slightly below the text in front of it. That's what a subscript is. So y equals the log base b of x is the same thing as b to the y equals x. The function f of x equals the log base b of x is the logarithmic function with base b. All right, so let's do a little practice. Let's take a logarithmic function, logarithmic equation, and let's rewrite this as an exponential. All right, so the first logarithm we have here is 3 equals the log base 7 of x. So 3, what my logarithm is equal to, is my exponent. And what I'm going to raise to that exponent is my base, which is 7. And that's going to be equal to x. So 7 to the third is going to equal x. My base is 7. The exponent is what my logarithm is equal to. That's what the logarithm is. It's the exponent I raise a base to get that value x. So the equivalent to this is 7 to the third equals x. And you could find what 7 to the third power is. You could use your calculator and determine what that value is. Let's look at the second logarithm. We have 2. That's going to be our exponent, is equal to the log base b. So our base that we're raising to that exponent 2 is b of 25, and that's going to equal 25. So let's write that down. So our base is b, our exponent is the number 2, and that's equal to 25. So 2 equals the log base b of 25 is equivalent to b squared equals 25. So you should be able to determine what b is. B should be the number 5. And it's not negative 5 in this case because the base cannot be a negative number. So b could be, or b is, 5. So 2 equals the log base 5 of 25. All right, let's look at the last one. The log base 4 of 26 equals y. So again, y is the exponent that I raise my base to get the number 26. So in exponential form, our base is 4. We're raising that to the y power, and that's equal 26. And that's the beauty of logarithms, Because if you look at this form here, what do I raise 4 to get 26? I don't know. I had no idea. 2 point something? I don't know. But the log base 4 of 26, I can find that. And we're going to get a property later where we can easily find what the log base 4 of 26 is. As a matter of fact, your calculator can calculate the log base 4 of 26. So you can find what number you would raise 4 to get 26. It's going to be a decimal approximation, but you can find it. All right, let's try the other way. Let's take some exponentials and let's see if we can write those as logarithms. So I have 2 to the 5th equals x. Now remember, my exponent is what is my logarithm is equal to. So my exponent is 5. So we're going to write 5 equals log. My base is 2. Base 2, and that is a subscript. So it's to the right and slightly below the logarithmic text, the log. And that's going to be of x. Now you could determine what 2 to the 5th power is. As a matter of fact, it's 32. So 5 equals the log base 2 of 32. 5 is the power that you raise 2 to get 32. All right, let's write b to the 3rd equals 27. Again, my exponent is what my logarithm is equal to. So my exponent is 3. So we have 3 equals log. My base, in this case, the base is b. So we're going to write that as a subscript, slightly to the right and below my previous text, my log. And that's going to be of 27. So b to the 3rd equals 27 is equivalent to 3 equals the log base b of 27. And I do believe that base will be 3. Because what would you raise to the 3rd power to get 27? Well, that would be 3. So an equivalent statement to this one would be that 3 equals the log base 3 of 27. Because what do you raise 3 to get 27? You raise it to the 3rd power. All right, the last one. Well, there's that number e. Remember that number e from the first section? That's that natural number. It's approximately 2.7. And the reason we gave that number a name, we called it e, is because it shows up a lot in exponential functions of natural phenomenon. So we gave it a name and we called it e. All right, again, our exponent is what our logarithm is equal to. So our exponent is y, and that's equal to the log. Our base in this case is the number e, log base e of 33. Okay, let's evaluate some logarithms, which we were doing on the previous slide also. But you can evaluate logarithms by writing them as exponentials. So let's first look at the log base 10 of 100. Again, what is the logarithm defined to be? The logarithm is defined to be the exponent you raise that base to get that value. So the log base 10 of 100 is equivalent to 10 to some power is equal to 100. The logarithm is equal to the exponent you raise that base to, so our base is 10, we're raising it to some exponent, and we're going to get what we're taking the logarithm of, which is 100. Well, what do you raise 10 to get 100? Is that 2? 10 squared equals 100. So the log base 10 of 100 is 2, because what do you raise 10 to get the number 100? You raise that to the second power. All right, the next one's a little bit more complicated than the first one. Log base 5 of 1 over 125. So let's first write that in an equivalent exponential form. So our base is 5. And we're going to raise that to some exponent, which I'm just denoting with a question mark. And that's going to be equal to what I'm taking the logarithm of. So to be able to determine what this exponent is, I need to rewrite 1 over 125 as an exponential with a base of 5. So can I write 125 as 5 to a power? And the answer is yes. 125 is 5 to the third. 5 times 5 is 25, times 5 is 125. So I can write this as 1 over 5 to the third. Now, from the laws of exponents, if I have a number raised to a power in the denominator of a fraction, I can take that to the numerator by changing the sign of the exponent. So I can write 1 over 5 to the third as 5 to the negative 3. They're the same thing. Remember that negative means to take the reciprocal of that number raised to that power. So 5 to the minus 3 is equivalent to 1 over 5 to the third, which is equivalent to 1 over 125. So now, what exponent do you raise 5 to get 1 over 125? And the answer is negative 3. So the log base 5 of 1 over 125 is negative 3. Because what do you raise the base 5 to get 1 over 125? Well, you would raise it to the negative third power. All right, how about this one? The log base log base 36 of 6. So again, let's write this as an exponential. We have 36 is our base. We're going to raise that to some power, which I'm just denoting with a question mark. I could certainly, instead of using a question mark, use the variable y. That might be easier for you to see if you write a y instead of a question mark. Okay, and that's going to be equal to 6. So again, what is the logarithm equal to? It's equal to the exponent you raise that base to get that value. So log base 36 of 6 is equivalent to 36 to some power equals 6. Well, what would you do? What power would you raise 36 to get 6? Well, I could take the square root of 36 to get 6. That's true. And again, how do we write the square root in terms of an exponent? The index, which is 2, is the denominator of our fraction. So we're going to, the equivalent of the square root of 36 is 36 to the 1/2 power. So the log base 36 of 6 is equal to 1/2. Because what do you raise the base 36 to get 6? You would raise 36 to the 1/2 power to get 6. So this is very similar. What do you raise 3 to get the 7th root of 3? Well, I could rewrite the 7th root of 3 as 3 to the 1/7. So now, if I wrote this as an exponential, what do I raise my base 3 to get 3 to the 1/7? 1/7? So the log base 3 of the 7th root of 3 is equal to 1/7, which is going to lead us to one of our basic properties of logarithms here in a minute. You'll notice that the base of my logarithm and the base of that exponential that I'm taking the log of are the same number. I have log base 3 of 3 to an exponent. So let's continue our discussion and get those basic properties of logarithms. So the first basic property we have of logarithms is that the log base b of b is 1. That's because 1 is the exponent you must raise that base b to get b, or in exponential form, b to the first power of b. So the log base b of b is always the number 1. So the log base 2 of 2 is 1. The log base 3 of 3 is 1. The log base 4 of 4 is 1, etc. The second basic property we have of logarithms is that the log base b of 1 is 0. So anytime you take the logarithm of the number 1, you get 0, because 0 is the exponent to which that base b must be raised to get 1. You know that if you raise any real number except 0 to the 0 power, that is equal to 1. So the log any base of 1 is 0. It doesn't matter what the base is. If you're taking the log of 1, you're going to get 0. All right, so what's the log base 9 of 9? Well, that's just going to be equal to 1. The log base b of b is equal to 1. And what's the log base 8 of 1? Well, anytime I take the log of 1, I get 0. It doesn't matter what the base is. All right, so we have a couple of inverse properties of logarithms. The first one we use all the time. The second one, maybe not so much. The first inverse property says that the log base b of b to the x is x. And if you think about the definition of the logarithm, that makes sense. Because what is the logarithm equal to? It's equal to the exponent you raise your base to get that value. So what would you raise b to get b to the x? X. The second inverse property is when I raise my base to the log base b of x, I get x. Okay, so then what's the log base 7 of 7 to the 8th? According to my first basic inverse property of logarithms, that is just equal to 8. Because what do I raise 7 to get 7 to the 8th? Well, 8. And what's log base 3 of 17? If this base matches the base of the logarithm, then this is just equal to 17. All right, let's talk about graphing the logarithmic function. So let's recall from the previous section, we did graph the exponential function 3 to the x. So we set up a table and we picked 4 values for x, and we evaluated our function, and we got 4 ordered pairs that we plotted on the coordinate plane. If we pick the value for x of -2 and we evaluate the exponential function at -2, 3 to the -2 is 1/9. If we evaluate the exponential function 3 to the x at -1, 3 to the -1 is 1/3. If we evaluate at x equals 0, 3 to the 0 power is 1. And if we evaluate that function at the first power, 3 to the first power is 3. All right, now let's look at the logarithm. Well, first of all, the exponential and the logarithm are inverses of each other. So if we graph g of x equals the log base 3 of x, that is the inverse of our exponential 3 to the x. So we would anticipate that the x and the y coordinates would interchange. But let's check to make sure. So we're going to find points for our logarithmic function by choosing 4 x values. And you can see that we chose wisely. So if we input 1/9 into our logarithmic function, the log base 3 of 1/9 is -2. Because what do you raise the base 3 to get 1/9? Well, it would have to be -2. Let's evaluate the logarithmic function at 1/3. So if I evaluate the log base 3 of 1/3, that's going to be equal to -1. Because what do I raise 3 to get 1/3? Well, it would have to be to the -1 power. And if I evaluate the logarithmic function at 1, the log any base of the number 1 is 0. And if I evaluate the logarithmic function at 3, the log base 3 of 3 is 1. So you should see, looking at our exponential function, my x's were -2, -1, 0, and 1. And in my logarithmic function, those are my y's. That's what inverse functions do. They interchange domain and range, x and y. And if you look at the range or the outputs of my exponential function, 1/9, 1/3, 1, and 3, those are the inputs of my logarithmic function, because that's what inverses do. They interchange domain and range. They interchange the x and y's. All right, let's see if we can plot these now. I have a sharing issue, so I'm going to reshare. There we go. All right, so we did plot the exponential function 3 to the x in the 4.1 video. So we did plot that, and we saw what it looked like. The x-axis is a horizontal asymptote. The y-intercept is 1. All right, now let's look at the logarithmic function, and this is going to lead us to some general definitions of the graph and the domain of the logarithmic function. Since the logarithmic function interchanges the coordinates on the exponential function, it's the inverse, so we interchange the x and y's. Instead of going through 0, 1 like the exponential function does, it's going to go through 1, 0 because we interchange the x and y's. So the exponential function has a y-intercept of 1. The logarithmic function has an x-intercept of 1. The exponential function went through 1, 3. So the logarithmic function is going to go through 3, 1. So you can see the graph there of the logarithmic function. Now, the exponential function had an horizontal asymptote of the x-axis. So the logarithmic function will have a vertical asymptote of the y-axis. So you can see, again, let's talk about the domain and range. The domain of the exponential function is the set of all real numbers. Let's write that down. But the range, because there is no exponent you can raise a base to and get 0, the range was the set of positive numbers. So if we're interchanging domain and range to get the logarithmic function, because the logarithmic function is the inverse of the exponential, then the logarithmic function's domain is the range of the exponentials, and its range is the domain of the exponential. So what this tells you is you cannot take the logarithm of a negative number. You cannot take the logarithm of 0. The domain of the logarithmic function is the set of positive numbers. So you're only able to take the logarithm of a positive number. So here are characteristics of the logarithmic function in the form f of x equals the log base b of x. The domain of the logarithmic function f of x equals log base b of x consists of all positive real numbers, or the set from 0 to infinity. The range of f of x equals the log base b of x consists of all real numbers. The graphs of all logarithmic functions of the form f of x equals the log base b of x pass through the point 1, 0, because f of 1 equals the log base b of 1. We've got a 1 missing right there, and that is equal to 0. So the x-intercept is 0. There is no y-intercept. The y-axis is a vertical asymptote. If b is a number larger than 1, f of x equals the log base b of x has a graph that goes up and to the right and is an increasing function. If the base is a number between 0 and 1, and it could be, f of x equals the log base b of x has a graph that goes down and to the right and is a decreasing function. The graph of f of x equals the log base b of x approaches but does not touch the y-axis. The y-axis, or x equals 0, is a vertical asymptote. So the domain of an exponential function of the form f of x equals b to the x includes all real numbers, and its range is the set of positive real numbers. Because the logarithm function reverses the domain and range of the exponential function, the domain of the logarithmic function of the form f of x equals the log base b of x is the set of all positive real numbers. In general, the domain of f of x equals the log base b consists of all x for which, and this is some kind of typo here, for which x is greater than 0. Or we could write this as the log base b of g of x. And in that case, then g of x would be greater than 0. What we're saying is that what you're taking the log of, whatever that expression is, it has to be greater than 0. You cannot take the logarithm of a negative number. You cannot take the logarithm of 0. So whatever your expression you're taking the log of, that has to be greater than 0. And we can use that to find the domain of a logarithmic function. So what's the domain of f of x equals the log base 4 of x minus 5? Well, this is the logarithmic function, base 4, that's been shifted to the right 5 units. Remember, when you subtract a value from your input x, when you subtract, that is a shift to the right. So if you think about this, the entire graph gets shifted to the right 5 units, including the vertical asymptote, including the domain. Everything gets shifted to the right. So how do you find the domain of a logarithmic function? You take whatever expression you're taking the log of and set it greater than or equal, set it greater than 0, not greater than or equal to, greater than 0. Because what you're taking the log of must be a positive number. Solve the resulting inequality. So any value greater than 5, you can take the log of. You cannot take the log if x is 5. You cannot take the log of 0. You cannot take the log if x is less than 5, because that would mean that value would be negative, and you can't take the log of a negative number. So the domain of this function is all the numbers to the right of 5. And if you graph it, as I said, when you subtract 5 from x, that is a shift to the right. Everything gets shifted to the right. The vertical asymptote gets shifted to the right, as does the domain. So the domain of this function is going to be all the numbers to the right of 5, or from 5 to infinity. Here are all of our translations, or transformations of our function. These are the same transformations we've had all along. If I add a constant to the logarithmic function, that's a shift up. If I subtract a constant from the logarithmic function, that's a shift down. If I add to the input x, that's a shift to the left. If I subtract from the input x, that's a shift to the right. It also shifts the asymptotes, the vertical asymptote. If I multiply the logarithm by a -1, that is a reflection about the x-axis. If I multiply the input by a negative, that would be a reflection about the y-axis. If I multiply the logarithm by a constant, that is either a vertical shrink or stretch, depending on the value of what I'm multiplying it by. If c is bigger than 1, it's a vertical stretch. If c is between 0 and 1, that is a vertical shrink. And if I multiply x by a constant, that's either a horizontal stretch or shrink, depending on the value of c. If c is greater than 1, that's a horizontal shrink. If it's between 0 and 1, that's a horizontal stretch. All right, so our two most used logarithms. The first is the common logarithm. And the common logarithm is the log base 10. And on your calculator, this is the button that says log. That is the common log, or log base 10. So on your calculator, log is the log base 10. So let's see if we can't use the logarithm on our calculator to determine a value. The percentage of adult height attained by a boy who is x years old can be modeled by f of x equals 29 plus 48.8 times the log of x plus 1, where x represents the boy's age from 5 to 15. And f of x represents the percentage of his adult height. Approximately what percentage of his adult height has a boy attained at age 10? So you are looking for the value of the function when x is equal to 10. X is the age of the boy. F of x is the percentage of his adult height. So we're wanting to evaluate f of 10, and that's going to be 29 plus 48.8 times the log of 10 plus 1. And I can go ahead and add 10 and 1 and get 11. So this is 29 plus 48.8 times the common log of 11. And I said I was going to write 11, and I wrote 10. Cut that. All right, so now I need to use my calculator to calculate this. And my calculator can calculate log base 10. So I'm going to share my calculator. All right, so we had 29 plus 48.8. And now we need to find our logarithm. And over here on the left, you can see log. Now, that's lowercase. Some of your calculators may actually have it in an uppercase form, which is actually more convenient or more understandable, because you could mistake that lowercase l for a capital I. It is not. It is an L. So we're going to click the log button, and you'll notice that when I click the log button, it opens parentheses for me. So if I needed to put an expression in here, take a logarithm of an expression, I could certainly do that. I'm going to type in the 11, and it's really important that you close your parentheses. It's just a really good habit to get into. But if you don't close them and you have something else going on to the right here, maybe you're adding a value or subtracting a value, your calculator will not know that that's not supposed to be inside the logarithm. So make sure you close your parentheses. So do I have that typed in correctly? 29 plus 48.8 times the log of 11. So I'm going to hit enter, and I get about 79.8, 80%. Okay, so what does this mean? This means that by age 10, most young men have reached 80% of their adult height. Okay, let me go back and share my PowerPoint. All right, so we got approximately 80%. All right, the next logarithm that you have available on your calculator is the natural logarithm. And I guess I need to go over some properties. And any properties that hold for any base will hold for the common logarithm. So if you have log base b of 1 is 0, the log base 10 of 1 is 0, etc. All right, so the natural logarithm. The logarithmic function with base e is called the natural logarithmic function. The function f of x equals the log base e of x is usually expressed as f of x equals ln x. And this is an L. And you might wonder, why is she overemphasizing that that's an L? Because one semester, many years ago, I had a student who typed in all of his natural logarithmic functions into MyMathLab using a capital I. So he got every single solitary problem incorrect. So that is an L. It is not an I. All right, the properties of logarithms for any base hold for the natural logarithm. The natural log of 1 is 0. The natural log of e is 1. The natural log of e to the x is x. And these come in quite handy, these two right here, especially when we start solving equations in the next couple of sections. So the natural log of e to the x is x, because the natural log is the log base e. The log base e of e to the x is x. All right, so when the outside air temperature is anywhere from 72 to 96 degrees Fahrenheit, the temperature in an enclosed vehicle climbs by 43 degrees in the first hour. The function f of x equals 13.4 times the natural log of x minus 11.6 models the temperature increase f of x in degrees Fahrenheit after x minutes. Use the function to find the temperature increase to the nearest degree after 30 minutes. So you're wanting to evaluate this function at 30. X is the number of minutes. F of x will be the temperature increase. Okay? So we're going to evaluate this function at 30. Okay, so what we want to calculate is 13.4 times the natural log of 30 minus 11.6. So let's go back to our calculator and let's calculate this. All right, so we're going to take 13.4 times the natural log of 30. So the natural log, ln, is right below the common log. So we're going to click the ln button, and again, you can see that it opens my parentheses. So I'm going to type in 30. And now it is very important that I close those parentheses. If I don't close those parentheses and then I subtract the 11.6, my calculator will assume that what you're taking the log of is 30 minus 11.6. You must close those parentheses so that your calculator knows it's taking the natural log of 30, multiplying that times 13.4, and then subtracting 11.6 from the result. So I'm going to hit enter, and I get approximately 34 degrees. So what's this mean? Let me go back and share my PowerPoint. All right, so we got 34 degrees. And that's 34 degrees Fahrenheit approximately. So this is one of those cases where you see how important it is not to leave something in your car, like an animal or a child, or even you just can't do it. Because even if 72 degrees, which is relatively cool, after 30 minutes, your car's inside temperature has already risen to 106 degrees. That's too warm for any living thing. And it's even worse if it's 96 degrees, then the temperature inside your car is 130 degrees. So this is a good reminder that you should not leave anything that you care about in your car when the temperature is warm. All right, that concludes section 11.2 on the logarithmic function.